We are now live, we're recording so that I can put this on YouTube for you. So if we want to change these questions up a little bit, I can give you all the information at once. Okay, we've got Noah pulling Sam across some sand in a toboggan. Coefficient of kinetic friction between the toboggan and the sand is 0.3. Sam and the toboggan have a combined mass of 90 kilograms. Noah's pulling with a force of 450 newtons at an angle of 40 degrees. How fast is Sam moving after 5 seconds? Now, this question, the thing to notice with this question is how fast, okay? Which means that is, whoa, that is not what I tried to say, okay? That is kinematics, right? We want how fast is it moving after t equals 5 seconds, okay? Now, in order to solve these types of kinematics questions, we need our acceleration, right? And how do we get our acceleration? Well, I think it's pretty clear based on the unit we're doing. We need to use dynamics, okay? Use dynamics to find our acceleration. Once we find our acceleration, we can go back to kinematic. It's like Russian dolls, right? You know those dolls that are like, they're like stacked inside of each other. You take one out, there's another one, you take another one out, blah, 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 right? That's what these questions are. I just keep adding layers to it. Or it's like an ogre, because ogres also have layers, like an onion, right? Ogres are like onions, okay? Bonus marks if you get that reference. So, first step of a dynamics question, free body diagram. Okay, there we go. There is our free body diagram. It's beautiful. What's going on here? Well, there's contact. We know that. So there's the force of gravity. There's the normal force. We know we've got some friction. We are pulling with some applied force there, but we need to break that up like so into an FAX. And I don't like where this FN went. I'm going to put it over there because we need an FAY component. Okay. So how do we break this up? We know this already. We're pretty good, right? Our triangle, our trigonometry. There's my triangle. So we know that Noah is pulling with 450 newtons at 40 degrees, which means my FAX is going to be 450. Oops, I forgot my equal sign. 450 times the cos of 40 degrees. So my FAX is equal to, do I have this number already? Do I have this number? Maybe, possibly. 344 newtons, 344.7 newtons. And my FAY, pretty much exactly the same. Sine of 40 degrees, which is 289 newtons, okay? Whenever you see a force at an angle, you should just jump to that, okay? You're gonna need to do that anytime you have a force at an angle. So there we go. You can highlight them if you want, just so that you don't lose that information. Now that we've got our applied force, our components, we need to go to our free body diagram. Now, in my head, this is the process that I think of. I know that there's friction, okay? And in order to deal with friction, I need my normal force, right? And if I need my normal force, then I need to use and look at the sum of the forces in the y direction, okay? Because I can't do friction without my normal force. So that's where I'm gonna start. The sum of the forces in the y direction. Well, what are my y components? I've got Fn, Fa going against the force of gravity. So Fn plus Fay minus the force of gravity. And I can jump, I'm going to start skipping a little bit of steps. The y direction is pretty much always equal to 0, unless the question's telling you the thing's moving upwards. It's equal to 0 since it's not moving vertically, right? It doesn't say that Noah is lifting Sam up off the sand. they're pulling across the sand. So there's no vertical motion, okay? Which means we can go ahead and solve this to say that our normal force is Fg minus Fay. And now, depending on the question, you might not have enough information to throw in here, but we know our applied force, we know our force of gravity, so let's just go ahead and punch these numbers in, right? Mg minus Fay, which is gonna tell us it is a 90 kilograms, right? 90 kilograms times 9.81 minus 289, which means our normal force is going to equal dun, 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 593, right? 593.6 according to my notes. Okay, so there is our normal force. Okay, and again, I'm going to highlight this. It's not the answer, but just so we don't lose it. Because now that we have our normal force, again, my brain's always thinking one step ahead. We can find the force of friction now, and that makes us happy. Okay, we're looking for acceleration after all. So now let's go to the sum of the forces in the x direction, in which case all we have is Fax minus the force of friction, right? We're looking at this right here, Fax minus the force of friction, okay? And this is gonna equal mass times acceleration. Oh my goodness, I'm out of room already. How did that happen? Okay, that's gonna equal mass times acceleration. We are looking for our acceleration, so we can just take our acceleration and we can divide by the mass. So Fax, which we know, minus mu Fn divided by our mass, right? There is our friction. And we already found our normal force. Our normal force came from that, like, oh my goodness, see how it's all connected? So we know everything here. So we can just go ahead and say, well, all right, this acceleration is going to be my applied force, which is 344.7 minus 0.3 times our normal force of 593.6, all divided by this 90 kilogram mass, which means the acceleration, dun, 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 is a beautiful 1.85 meters per second squared. Okay. Again, not done, but we're there. I'm just going to double check this value. Maybe somebody at home has already done it. 0.3 times 593.6 divided by 90. Boom, 185. Beautiful. Okay, right? So now that we've got our acceleration, but we are not done the question. Remember, the question asked, and we'll go to pink, right? The question wants to know how fast. Okay, how fast when our time is 5 seconds. So V final is equal to V initial plus AT. We know we start from rest. That's beautiful. So our final speed is just going to be our acceleration times the 5 seconds, which gives us a final speed of 9.25 meters per second. And that right there, we can put a box around it. We can highlight it. That is our final answer because that's what the question asks for. Okay, 9 meters per second, that's pretty fast, right? That's super, super fast. In reality, 5 seconds is a long time to be applying that force. You're probably not going to apply it for that long. But if you do, right, acceleration adds up really, really quickly. Okay, so again, this is a very typical question. Okay, break up a vector into its components, look at your free body diagram, find your normal force, use your normal force to find your friction, use your friction to find your acceleration, use your acceleration to find some kinematic value, be it distance, time, acceleration. All right, I'll give you some of the values. You need to find the other one, okay? We could do this backwards. We can do this completely backwards, where instead I could get rid of, I could give you this. I could say, hey, he pulls them for 5 seconds and is traveling at 9.25 meters per second. What force are they pulling at? So you need to use this value to find your acceleration, then use your acceleration to find your applied force, use your applied force then with the angle to find your actual force, right? You can do this. You can do this completely backwards. It's the exact same question. Okay. Cool. I love this stuff. This stuff's so much fun. So good. We only have one more question left. One more. Oh no. Oh no. Okay. So cutting the grass. Seems how it rained yesterday. It's supposed to be beautiful this week, and I'm sure some of you might be cutting the grass at home. That's fantastic. So we want to know. We're saying, okay, couple things here. We're given a mass. We're pushing down on the handle of the lawnmower with a force of 200 newtons at an angle of 65 degrees with the ground, okay? First thing, moving across the lawn with constant velocity, determine the coefficient of friction, okay? And then now we're gonna assume something different in part B. So first step is find the coefficient of friction. This coefficient of friction is our mu value, okay? So couple things about this question, okay? Pushing down is important to is an important distinction to make. If you push down on something, you are going to increase the contact. So if we draw our free body diagram, something like so, well, okay, before we even jump to that force, we know that there is going to be a force of gravity going down and the normal force going up, okay? Now, there is a force being pushed downwards, which means if you're thinking about this, and again, I'm gonna draw this, don't necessarily draw this. This is the handle of the lawnmower, like that, right? There's the handle, there's our person pushing downwards on this handle, which means we don't like drawing with angles with the arrows pointing towards there. That's bad. Remember, we don't like that. We like to see the arrows going away. So in reality, what we have is this applied force going down at an angle like that, okay? Which means if we look at the components of this, we're gonna get an FAX component pushing it forward, just like we did in the last question, but the FAY is now pushing down, okay? And that's gonna change things up for the normal force. We're increasing the contact of the lawnmower and the ground, okay? We're missing one more thing, okay? We're looking for the coefficient of friction, which means chances are there's friction. So we need to go ahead and add in our friction there. There we go. It's beautiful, okay? So, couple things here. We should probably figure out what the heck our force components are because we know this thing, right? They're pushing with 200 newtons and it tells us 65 degrees with the ground. Here's the ground, okay? There's our FAX. There's our FAY, okay? I'm just gonna jump to the values because we're smart cookies now. We've got an FAX of 84.5 newtons and we've got an FAY of 181.3 newtons. Okay, you should be able to find those components, no problem. It's just SOHCAHTOA. Okay, fantastic. Why do I have no room to do this question? I must have messed up. Okay, so I just need to shrink this stuff. Bear with me. I'm going to shrink this up here. Okay, I'm also going to shrink this beautiful picture up over here. There we go. Okay, so since we are looking for a coefficient of friction, since we want this, in order to find that, we need our normal force. Okay, you just have to find it. Okay, so our normal force, let's go ahead and look at the sum of the forces in the y direction. We've got Fn going up but now we have two forces going down, the force of gravity and our y component of our applied force. Okay, so if we do this, solve for our normal force just like we did, mg plus fay, which is going to equal to our mass, which is 25 times 9.81 plus 181.3 newtons, we are going to get a normal force right here. That's beautiful. It's 426.6 newtons. Okay, again, highlight, not the answer, but it's our normal force. We are increasing this, we're making this huge normal force compared to just what gravity would be on its own. Okay, so now that we have the normal force, we need to do something with friction, which means we need to look at the x direction. Okay, so in the x direction, what we've got going on here, we've got the sum of the forces in the x direction. Well, we've got our applied force, we've got our force of friction, so all we have Fax minus the force of friction, okay? And that's going to equal mass times acceleration. We're missing one thing, the acceleration. Anybody have an idea? I'm going to toss it in the chat. What's our acceleration? Some little tiny hidden hint in the question. Why would acceleration equal 0? Constant velocity. Ding, 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 ding. Constant velocity, right? Anytime you see a constant velocity, right away, you should be thinking your acceleration is 0 meters per second, okay? Which means this whole thing cancels out. So really, our force of friction is just going to equal our applied force, right? That's all that's happening here, okay? But our force of friction, we're not looking for our friction, we're looking for our coefficient of friction. So let's say mu Fn is equal to our applied force in the x direction. Well, if we take a look at this a little bit closer, right, we know that, we know our normal force, because that's just our pink thing right here. So we are just perfectly happy in saying that this coefficient of friction is just going to be our applied force in the x direction divided by our normal force, which is going to be 84.5 divided by 426.6, which should give you an answer of 0.20. Okay, yay, we can put a box around that. We're happy about that. There is our answer. One thing that I don't think I clarified in when we were talking about friction, there is no units on the coefficient of friction. Okay, there's no units. It's just a value. Okay, no units. Little thing about this question, since you're looking for the coefficient of friction, if you got an answer of like 5, you did it wrong. Okay, if you didn't get a decimal, if you got a large number, even just 2, 1.5 even, you did it wrong. Okay, your coefficient of friction should always be small. It should be small. Okay, that's just a nice little check to make sure you did it right. Okay, so now in part B, last question for the day. Now we're changing up the force they're pushing with. They're pushing with 280 newtons. Okay, we want to know how long does it take them to travel 20 meters if they start from rest, and we're going to assume the friction is the same that we found in part A. So we know that our coefficient of friction is 0.20. So this question is pretty much exactly the same, right? Except we're just changing up the force, right? So this question is exactly the same, but now our applied force in the x direction is, or sorry, our applied force, not in the x direction, our applied force in general is 280 newtons, and acceleration is not equal to 0 meters per second, right? Chances are, since we want time, it's asking us how long we're going to travel a distance, we need to find this non-zero acceleration, right? I have that arrows done. We need to find the acceleration, okay? Because that will help us figure out how long. So I always like to say work smarter, not harder, okay? All of this stuff is exactly the same. Boom, just like so, okay? It is exactly the same, but now our components are gonna change because now we're not pulling with 200 newtons, we're pushing with 280 newtons, 280 newtons, which means we are going to get a y component of 253.8 newtons and an x component of, where is my value, 118.3 newtons. So comparing to part A, right, here 84 to 181, 118 to 253. It went up a little bit because our force went up a little bit. That makes perfect sense, okay? The other thing that doesn't change, right, is our normal force. The sum of the forces in this y direction here, this pink normal force, this stuff is going to be exactly the same, right? We're not changing any forces. We just changed how much force. So we still the same mass, still the same everything, but now we can replace our FAY component with 253.8, right? Which means that's going to change what the normal force is. This normal force, our new normal force, is probably going to be a little bit higher. It's actually 499 newtons. Again, little highlight so we don't lose it. It's increased a little bit because this applied force increased a little bit because our applied force, okay? So we've got a larger normal force. In the x direction, things change a little bit, just a little bit, because the sum of the forces in this x direction is still FAX minus the force of friction, and that still equals mass times acceleration, but now that acceleration is not 0, okay? It was 0 in part A, it's not 0 anymore. So we need to solve for that. So our acceleration is our FAX minus this force of friction divided by our mass. Our force of friction is really nice because we know our mu and we know our normal force, right? We know that this force of friction, and you're going to memorize this formula, the force of friction is equal to mu Fn, which is equal to 0.2 times our normal force, which we already found, 499. Okay, so we can go ahead and toss all those values in. Our FAX is now 118.3. Our force of friction is 0.2 times 499. And we're going to divide that by this 25 kilogram lawnmower, which means our acceleration is going to be dun 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 0.74. Okay, there's our acceleration, 0.74 meters per second squared. Pretty small, which makes sense. You're cutting the grass, you're not running a marathon. It's weird. Never seen someone run while cutting the grass. It's very strange. Okay, but we're not done the question, right? Remember, we're never done the question because the question asked us how long, okay? So how long does it take us to do all this? Well, turns out I don't know how to write small. So I just need to shrink this. Bear with me for a second. I'll take this too. Shrink that up a little bit. Now we want to know how long it takes to travel 20 meters, right? We want the time when the delta x is equal to 20 meters. So our beautiful formula, right? Delta x equals 1/2 AT squared. Since we started from rest, that's totally cool. So T is going to be 2 delta x divided by our acceleration. Take the square root, the positive one. We know what our acceleration is. I ran out of room, so I'm not going to punch those numbers in, but you should get 7.4 seconds. And that right there is our final answer. Whoo-wee. Love it. Good stuff. Love it. So much fun. Okay. Right. Very, very similar, very, very typical questions. It looks like a lot of work. Um, it's really not. I'm doing a lot of like writing and stuff here. But you're gonna follow these same steps for every question. Draw your free body diagram, get your FAX, FAY from it, and then just use the equations. Here's a little trick. If there is no friction, you do not care about your normal force. Unless the question's specifically asking for it, you really could not care less. What you care about will be in the x direction. But as soon as there's friction, now you need to find your normal force. Okay, so just a little thing to be careful about. Okay, so I'm going to send you another poll. I want to know how you're all feeling now. Okay, now that you've seen me go through 2 more examples, I'm curious to know if it changed at all. I'll stop this share. There, sorry, I want to stop the recording.